Hello dear students. Now in this lecture we are going to discuss about the electronic spectra in transition metal complexes. In our previous lecture we have discussed about the selection rules of the transitions in metal complexes. The lecture plan for this lecture is term symbols, as I have told you earlier. The calculation of term symbols, how we can calculate the term symbols for the different types of systems. Now ground state term symbol calculations for P2 system and the ground state term symbol calculation for the D2 system, which is of immense importance for the transition metal complexes. Now come to the term symbol. As we have discussed earlier, these are used to represent the electronic configuration of a particular energy state and the resultant angular momentum L of an atom. Term symbols can be given through this value 2s plus 1 L j. S is the total spin angular quanta number. J is the total resultant angular quanta number. This is the table for L and state values. 2s plus 1, which indicates the spin multiplicity, and it plays an important role. If the spin multiplicity is greater than 0, then the spin value would be different. If spin multiplicity is 0, then the 2s plus 1 value would be 1, and the different L values located for 0, 1, 2, 3, 4, 5, 6, these can be arranged according to their state values. Means for L is equal to 0, state would be S. For L is equal to 1, the state would be of P, and for L is equal to 2, 3, 4, 5 and 6, the respective state would be given D, F, G, H and I and so on. How we can calculate the term symbol? First, determine the possible values of ML and MS. Determine the configuration that follows Pauli's exclusion principle, which is a necessity, and set up a chart for the microstates that we have to calculate. Resolve the chart of microstates into appropriate atomic states. The construction of a microstate table. For example, carbon P2 system. The electronic configuration of carbon is 1s2, 2s2 and 2p2. The microstates corresponds to the various possible combinations of electrons within the px, py and pz orbitals. The P2 system, the two electrons of p orbital can be arranged in different ways. It means 2 electrons in px and py, 2 electrons in py or pz, 2 electrons px, pz. There are so many different ways in which the 2 electrons can be arranged in 3p orbitals. For a carbon atom, Ml will range from +2 to -2, and Ms can have a values of +1, which means the both electrons are pointing upward. For Ms is equal to 0, one electron is pointing upward and the other electron is pointing downward. For L is equal to -1, the both electrons are pointing downwards. For Ml is equal to 2 value, it will range from +2 to -2. It means the L value will go from +2 to -2. The configuration that a carbon atom in its ground state can adopt like this, means the 2 electrons are arranged in px and py orbitals. For this, the Ml values, summation of Ml will give 1. It means the summation of Ml is equal to +1, and for this electron Ml will be equal to 0. These two Ml values are adding up and will give a Ml of 1, whereas the Ms value for this configuration would be +1, means these two electrons are pointing upward in different atomic orbitals. First, the Ms value is of +½ and second electron will have a value of -½ These two +½ values will be add up and will give 1 for Ms. For the second configuration, if the two electrons are arranged in py and pz orbital, it means the Ml value is of -1 and the Ms is of +1, which comes from plus half and plus half for both the electrons. For the third configuration, the ms value is of plus 1 value because both electrons are pointing upward, means in the same direction, and contributes plus half for the arrow pointing upwards, and the ml will be given by this is equal to 0, means the plus 1 and minus 1 add up will give ml value of 0. These are examples of some of the ground microstates. Other would have the electrons pointing downward. This is an example of carbon atom in excited state. Here the two electrons are in same orbital and one is pointing upward and other one is pointing downward. It means it will contribute for ml is equal to 2, means plus 1 and plus 1 for each electron. For this the ms value would be 0 because plus half and minus half will give a value of 0 for ms. For the second configuration, if both the electrons are situated in a py orbital and these two electrons situated in py orbitals, for ms they will contribute a 0 and for ml value also 0. For the third configuration, the ms value is also 0 because both the electrons are in same orbital, whereas for ml the value would be of minus 2. These are the examples of excited microstates. There are 15 possible microstates for P2 system, and the resultant values of ml and ms obtained for this P2 system like this. Here ml plus 2, the electrons are arranged in opposite direction to each other but in a same orbital. This is the electronic configuration for P2 system if ml is equal to plus 2. For this system ms would be 0 because both the electrons are arranged in an anti-parallel fashion. Like this, ml is equal to 0. The electrons are again arranged in the same configuration in P2 system. Both the electrons lies in a same orbital. Similarly for ml minus 2, these two electrons are arranged in the same orbital. For the parallel fashion, ml would be plus 2 and the values of ml would be plus 1 for both the system. So these are 15 possible microstates, means the 15 possible configuration that a P2 system can attain within the 3 orbitals of P. The table includes all the possible microstates. Like in the previous table, ml plus 2 plus 1 0 minus 1 minus 2. For this ms plus 1 0 minus 1 means the two electrons are arranged in a parallel fashion, plus half plus half. Two electrons arranged in an anti-parallel fashion, means plus half and minus half, and the two electrons are arranged in pointing downwards, means ms becomes equal to minus half, and the superscript of plus and minus indicates that the electrons are arranged in
St, entropy of molar entropy of substance at temperature T, that is S0, that is molar entropy of substance at 0 Kelvin, plus integral term from, that is the change, this term correspond to the change in entropy for a substance when you heat the substance from 0 Kelvin to T Kelvin. So therefore, what you get this equation is very important equation in a way that if you know the value of S0 or S0, what is S0? S0 is basically the molar entropy of a substance at 0 Kelvin. So if you know the S0 and if you know the heat capacity of substance within the temperature range 0 Kelvin to T Kelvin, then what you can do is you can integrate this equation and you can determine the this contribution of second terms towards the molar entropy of substance at temperature T. So, question is, can you determine the first term S0, the molar entropy at 0 Kelvin? If you can determine it, then you can determine the molar entropy of substance at some temperature of interest, that is T. So, basically the third law of thermodynamics comes here into consideration. Third law of thermodynamics, it was just suggestion, it is just suggestion that is given by Planck. Max Planck suggested in 20th century, earlier 20th century, that he suggested that the molar entropy for a pure perfectly crystalline substance is 0 at 0 Kelvin. Why he suggested so? If you look at back to this expression of molar entropy of substance at temperature T, then what you get is molar entropy of substance at temperature 0 Kelvin. Added to this is the term from the contribution of change in entropy from 0 to T Kelvin. So, it is for sure that the entropy, since that, as we have just seen, we have seen that entropy increases with increase in temperature. So, it means this second term will always be a positive quantity, and entropy at any higher temperature will be greater than the entropy at absolute 0. That is, at absolute 0 Kelvin, the entropy should be least value for a substance. So, this led to the suggestion which Max Planck says that we can consider molar entropy of a pure perfectly crystalline substance at absolute 0 of temperature as 0, at absolute 0 of temperature as 0. So, with this S0 becomes 0, and that is how you can evaluate the molar entropy of a substance at specified particular temperature using this expression 0 to T Cp by T dt. But now the question arises, how to evaluate this expression? If we want to evaluate this expression, we have to make use of one of the law which relates the, that is de Bois law basically, which relates the heat capacities with that of some characteristic constants of the substances, and also as function of temperature. So, therefore, in a particular temperature range. So, therefore, making use of de Bois law, we can quantify the heat capacities, and we can substitute those heat capacity expression in this expression of entropy change, and we can determine a particular value of molar entropy at particular temperature. This is the way we determine a molar entropy of the substances at specified or particular temperature. So, this is how the third law of thermodynamics basically lays the foundation for determination of molar entropy at particular temperature, and that is how we say the third law of thermodynamics forms the basis of calculation of molar entropy of substance at particular temperature. So, in this lecture today, what we have covered is, we had started with consideration of entropy as function of temperature and pressure. We have derived a relationship for change in entropy with for particular change in temperature and pressure for all in general, that is general expression which is applicable for all substance. Then following which we have extended the derivations which we had done for temperature and volume, for the entropy change for temperature and pressure change, and temperature and volume change for ideal gases system, ideal gases. And then what we have done is, we have defined the standard state of entropy, and we have tried to observe that how we can determine the molar entropy of a substance at a specified pressure by making use of third law of thermodynamics. And if the pressure is 1 atmosphere, then what we can determine? We can determine molar entropy of substance at 1 bar pressure, and therefore, and in this way you can determine standard molar entropy of substance at 1 bar pressure, and if you know the value in this way, then you can determine the standard molar entropy of substance at other pressure. So, now the question arises, how to determine this molar entropy of substance at 1 bar pressure using Debye law. So, that will be the topic matter in the next lecture. In addition, we will also try to see what interpretation, physical interpretation, statistical interpretation of entropy has. So, with all this, we will with all these considerations and discussions, we will meet in next lecture. Thank you.
With this note, thank you, sir. Thank you so very much for giving us one another final session on chemical thermodynamics. I believe that all the students who might have watched this lecture would be benefited from it. And dear friends, if you have any queries, if you have any questions, if you want to give your feedback also regarding this particular lecture, then you can mail us at info.cc@nic.in. We would love to take your suggestions, and if you like to have a discussion or a lecture on a particular topic, then also you can mail us. And for viewing our lectures again and again, you can access YouTube, where we have a playlist with the help of which you can have a glimpse of these lectures on chemical thermodynamics, and very soon we are going to upload this lecture on YouTube only for you. We would be meeting again. Till then, take care. Goodbye. Thank you, sir. Thank you so very much.
Question number first, for a process from state 1 to state 2, heat transfer is in a reversible process is. Second question, which of the following is mostly neglected while doing calculating the work done? Question number third, integral of dq by dt is independent of reversible path connecting between the 2 points. Third, question number 4, integral of dq by t of a reversible path is given by. Question number 5, entropy is A. Question number 6, for any process which is undergone by a system, options are given below. Question number 7, for a reversible heat transfer and process being adiabatic, which of the following is true? Question number 8, the area under the curve TdS is equal to. Question number 9, which of the following statement is true? Question number 10, a pure substance which exists in a single phase has independent variables 0, 1, 2, 3. Which of the following relation is correct? Options are given below. The second TdS equation is given by. For getting TdS equation, we assume entropy to be a function of T and V and also T and P. True or false? Heat is transferred to a heat engine from a furnace at a rate of 80 milliwatt if the rate of waste heat rejection to a nearby river is 50 megawatt, not milliwatt. Determine the net power. Diagram given है और वहाँ से आपने power निकालनी है. Work done by a system is taken to be negative, positive. Thank you.
Welcome to module 17 of programming in C++. In this module, we will talk about friend function and friend class, trying to understand what do they mean and why are they useful in C++ design process. So, these will be the module outline. We will take examples of matrix vector multiplication and linked list, and finally, we will end with some notes. And as you know, as usual, the outline will be available on the left of your slide. So, let us first introduce the basic notion of friend function. On the left, you have the view of an ordinary function. So, the situation is like this, that I have a class, my class, which has some private data, it has a constructor, and it has a, I am sorry, just ignore this line, just ignore this line. I have this function written outside of this class, which is trying to do something with the class. What is it doing? It takes an object of the class by reference parameter, call by reference, and then it tries to print the data element component of that object. Now, what do we know? This is private. Therefore, if I have A, then I do not have, as a function outside, I do not have the rights to access this object. So, just consider this is not there. So, this will give rise to an error, and you will get an error of this kind, cannot access the private member declared in my class, because the reason you know very well by now is this is a global function and this is a private data. So, you cannot access this data directly. Now, let us look into the right hand side. In the right hand side, we have exactly the same code, except that we have introduced this in the class, much in the way we define the member function, but with a difference that this inclusion is prefixed by a keyword friend. Now, this does not make display a member function of the class. Display is not a member function of the class. It continues to be a global function, a special type of a global function, which is a friend of my class. But with this included, when I say that the display function, this global function display, which takes an object A of my class by reference and returns void, when I say that that is a friend of my class, then this does not remain an error, this error disappears. This is now allowed. So, the concept is like this, as if in our home also, if somebody would step in, we would normally allow them only to the drawing room, which is kind of the public space, and we will not allow them to the inner rooms, which is our private space. But if I have a friend stepping in, then I will probably not keep him in the waiting in the drawing room, rather I will take him to my inner rooms, my bedroom or kitchen and so on. So, it is like a similar concept. So, here he is saying that this function, the my class, is saying that the display function, which is outside of this class, which is not a member function, is still a friend, and therefore, the private data of this class will be exposed to this member. That is the basic idea of a friend function, and therefore, it will generate, like this will give a give a compilation error, but this will be a right output will be produced. So, with this let us see a formal definition of what a friend function is. A friend function of a class has access to the private and protected members of the class. That is, it can break the encapsulation. We have still not discussed what are protected members, but hold that for a while. When we discuss that, this will become clear, but they are pretty much like the private members only. So, it must have a prototype included in the scope of the class and must be prefixed with friend. We have just seen the example of the display function as to how do you write the signature of that function within the class with a friend in the front to say that this particular function is a friend of this class. Now, this function does not belong to the class, is not a member function, therefore, its name is not qualified by the class name as we do for normal non-friend member functions. It is not called with invoking an object, because it is not a part of the class, and a particular member function or a particular function can be friend of more than one class. Now, if we look at what all can be friend function, any global function could be a friend of a class, any member function of a different class. A member function of a different class could also be a friend of a class.